All right, unit 7, we're looking at the bonding and geometry of molecules. So we're looking at how do those molecules come together, and when they do come together, what shape do they take? That would be the geometry of it. So what shape do our molecules have, and why might they have that shape? So in order to look at this, we first need to look at the electron configuration, right? In the electron configuration, what it does is tells us exactly where our electrons are placed around the atom. And so when we talk about this, we look at it in terms of the quantum mechanical model. And what the quantum mechanical model does is it tells us that electrons are in probability zones. We call these orbitals, not orbits. Those are something different, all right? And their location is not exact. So think of it kind of like a border zone, all right? And you say somewhere within this zone, you will find electrons, all right? And we say their location is not exact. And why do you think that might be? Well, let's think about the speed of an electron. It's super, super fast, right? It's also really, really, really small. So because of its speed and super small size, it's impossible to find the exact location of an electron at any given time. By the time you think you've found the location of an electron, it has moved on somewhere else and is somewhere different, all right? So again, you never know the exact location of an electron at any given time. So those orbitals are just probability maps, or think of them as, like I said, the border space. Somewhere within this region, you will find your electron. And then you have your orbits, all right? Orbits are more so the exact position that that electron travels, all right? So the exact position of the electron within the atom. Think of it as a little snapshot of you throughout the day. If Google Maps were to take a little marker and make dots as you move throughout your day, and then at the end of the day, put all those dots together on one page, all right? So that orbit shows you the path or that exact position of the electron around your atom. So here, orbitals are probability zones, but orbits are exact, all right? Orbitals, probable. Orbits are exact. So in order to do this, we look at the quantum mechanic principal quantum number. And what that quantum number tells us is the energy level at which our electron exists, all right? And so each of these energy levels matches a period or row on your periodic table. Remember, periods go left to right, periods in sentences, which go left to right. So each energy level represents a period. So for instance, quantum number 1 or N1 describes the first energy level, and N2 describes the second, and 3 the third, and so forth. So it tells you at what energy level your electrons exist. Depending on what row on the periodic table your element is in, you will see all of those rows or energy levels illustrated in your electron configuration. And so within those energy levels, we see 4 different orbits. Those orbits are S, P, D, and F. All right, a little mnemonic to help you remember that is, it's easy to remember, but some people do forget S, P, D, and F. All right, and so when we look at our S orbital, it has a spherical shape. So imagine it like a ball. And it can hold a max of 2 electrons. Then you have your P orbital, which has a dumbbell shape. So what we call the dumbbell is, it looks kind of like an infinity sign. And that P orbital can hold a max of 6 electrons. So let's look at how it holds those 6 electrons. Each orbit can hold 2. So here's the first orbit. I add another electron. Here's another orbit. Now let's say I have a 3rd electron in my p orbital. So I'm going to have to add another one. Got 3 electrons. Now let's say I have 4 electrons. What am I going to do? Well, I go back and I double up. So there's 4 electrons, 5 electrons, and 6 electrons. So that is how your p orbital holds 6 electrons. It's got 3 orbits within it. right? And then you have your d orbital. You don't need to know the shape of it, but in case some of you are curious, it is a clover shape. But what you do need to know is that it can hold a max of 10 electrons. And then lastly, you have your f orbital, which can hold 14 electrons. All right, and just like the p orbital, each orbit within those can only hold 2 electrons. So then you've got 5 orbits within your d orbital and 7 within your f orbital. All right, so s can hold 2, p can hold 6, d can hold 10, and f can hold 14. You need to know those numbers. Remember, it's easy to remember, but some people do forget. S, P, D, and F. All right? So when you're writing your electron configurations, what you'll notice is that depending on what block in the periodic table that element is in, it will end in that respective orbital. All right? Your configuration will end with that respective orbital. So for instance, if we were looking at magnesium, as we're writing our electron configuration, which we're going to do here in a minute, and all of this will kind of come together, but we're looking at magnesium. My electron configuration should end with the s orbital. And if you remember, how many can s hold in total? S can hold 2 electrons. Well, look, there are 2 columns in the s block of the periodic table. So magnesium will end in S2. Because it's in the S block and it's the second row over. You notice, remember, P could hold 6. Well, let's look at our P block over here. All right, how many columns are in our P block? 1, 2, 3, 4, 5, and 6. And then we had our D, which could hold 10. And as you'll see, it also has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 columns in your D block. So see how those go together. And so you should be able to locate the elements based on its electron configuration because A, the highest energy level tells you the row which it's in. And then your orbital tells you which block. And the number of electrons tells you which column over it is. All right, so if we were looking at chlorine, it would end in P, and it's the 5th column over, so the last thing you would see would be P5. Its energy level, if we follow it over, it is in the 3rd row, 1, 2, 3, so 3P5. All right, so let's take a little bit more of a look at this. When we are writing our electron configurations, we must fill our orbitals from increasing energy levels. All right, so lowest energy to highest energy. Well, what order is this, you may be wondering? You're going to follow the order of the chart you draw. Because if you look at these numbers down below, I go 1s, 2s, 2p, 3s, 3p, 4s. Oh, look, I went back, 3d. Then I go 4, 5, 4, 5, 6, 4, 5, 6, 7, 5, 6, 7. What do you notice about that? None of them are in an order, right? It's kind of random. You don't want to have to memorize that. So up until 4S, it looks like you're doing good. It looks like you've got to order down. But then we at 3D, we start to get off and it starts to go in kind of a random looking order. So we're going to talk about how do you find that order. So in big, bold, underline, draw and follow your chart. All right, so how do we draw that chart? Taking a look at this here. Remember, you have 7 energy levels because there are 7 rows on the periodic table. And then you have 4 orbitals max per energy level. And so we're going to look at how do we get this path. And so if you'll follow along with the order that was written on the previous slide, we go from 1s, 2s, 2p, 3s, 3p. And remember, from here, it looked like we were doing good. But we don't go to 3D. We follow this arrow, and it takes us to 4s instead. So as you're doing this, you'll follow the arrows that go through the chart. So you will draw something similar to this, and you will follow those arrows. I refer to them kind of as follow the yellow brick road, except these are red arrows. Imagine they're yellow, just like the Wizard of Oz. Follow the yellow brick road. All right. As you're drawing this table, or even looking at this chart, you have these blaring red arrows in front of you. All right. You drew lines through your numbers for a reason, so please remember to follow them. Every year I see somebody draw all the arrows through their numbers, but then they still follow it in this order, left to right. This is a big no-no. All right, you must follow your arrows. Follow the yellow brick road. All right, so now that we have that down, let's figure out how to get this order. How do we make sure our arrows are straight and that they're going through the right numbers and the right orbitals? So on your piece of paper, on the left side, we're going to write our energy levels. Remember, there's 7 rows on the periodic table, so there's 7 energy levels. 1, 2, 3, 4, 5, 6, 7. And I have 4 orbitals. S, which holds 2, P that holds 6, D that holds 10, and F that holds 14. All right, and so we fill this out just like a Punnett square. Bring your 1 over and your S down. 1s2. Energy level 1 only has 1 orbital. Energy level 2 will have 2 orbitals. So 2s2, 2p6. Energy level 3 has 3 orbitals. 3s2, 3p6, 3d10. And what do you think level 4 is going to have? 4 orbitals, all right? So 4s2, 4p6, 4d10, and 4f14. Now, as you can see, we don't have a 5th orbital to go to, so 5 is going to stay with just 4 orbitals. So 5s2, 5p6, 5d10, and 5f14. From here, we start to make our way back down. All right, so bringing my 6 over, 6, and my s2 down, 6p6, and 6d10. Next level, 7s2, 7p6. All right, some of you may be wondering, why am I not writing them out? Like, why does 6 not have 4 orbitals? Why does 7 not have 4 orbitals? So we'll take a look at that once we get there. All right, let's first determine the path of your arrows as we go through the chart. All right, so in order to determine the path, we need to follow corner to corner in your chart. That's why you should draw, just like a Punnett square, your lines through it. All right, so corner to corner. Go back up to the top, corner to corner, corner to corner. Next one, corner to corner, to corner, to corner. Corner to corner. Please make sure you go through the corners, elsewise your numbers are going to follow the wrong path. You'll end up in the wrong box and you will have the wrong order. So make sure you're following corner to corner here. Corner to corner, corner to corner. Will help if you use a piece of graph paper. Oh, see, I got one crooked. So let's take it over here. Let's make sure it's straight. Corner to corner, corner. There we go. All right, and so there's your yellow brick road. Follow the yellow brick road. You have these big blaring arrows. Follow them, all right? They're there for a reason. And so as you're writing your electron configurations in a minute, you're going to place those electrons in order as we work our way through the table, all right? So our path, as we look at this, we're going 1s2. Then we go to the next arrow, 2s2. Go through the next arrow, 2p6, 3s2. Go to the next arrow, 3p6, 4s2. Then I come back, 3d10, 4p6, 5s2, and so forth as I work my way through the table. All right, so now let's put all of these little things together and let's talk about how do we write our electron configurations. What we're about to do is going to show us how our electrons are ordered in an atom in the specific way in which the atomic orbitals are ordered and are filled. And so as we're writing these, it's going to help you to know what does each of these notations stand for. So as you're writing it, the coefficient in the front represents your energy level, the energy level at which those electrons exist. The letter represents the shape of the orbital. Remember, we have our S, the spherical shape, and it can hold 2 electrons. We have our P, the dumbbell shape, which can hold 6 electrons. We have our D, but it's a clover, which can hold 10. And then our F, which can hold 14. All right, and so then we have our exponent. And that exponent represents how many electrons are in each level. All right, and so think of them as cups, and we want to fill them up as we go. And that exponent here tells us how much is in each cup as you move along. All right, once you fill the first one up, you move to the second one. As you move that one up, fill that one up, you move to the third one. And so one example that I like to use is think of it as marbles in a bucket. So we're going to go back to this, and over here to the side, I've drawn you 19 marbles. All right. And so I'm going to follow along through my chart and place those 19 marbles in the correct energy levels and orbitals which they should fill. All right. So if I'm looking at this, I always start where? I start at 1s. All right. And it can hold 2. So I'm going to go 1, 2. I've placed 2. Now I've got to keep moving. I get up here and I end up at 2s2. So that's my next cup. I can put 2 more here. That one's full. I've got to move to the next one. After 2s2, I go up here and I'm at 2p6. So this cup can hold 6. 1, 2, 3, 4, 5, 6. Now that cup's full. I've got to move to the next one. So I was at 2p6. Now I'm going to 3s2. 1, 2. Well, I still have marbles. And I want to place them all in buckets, so I've got to keep going. After 3s2, following along with me over here on the right, after 3s2, I come to 3p6. So again, can hold 6. 1, 2, 3, 4, 5, and 6. All right. Well, I have one lonely marble left to place. My P6 is full, so that means I've got to move on to the next one. After 3P6, I come to 4S2. Remember, following the yellow brick road. And so I have the potential to hold 2 electrons. But how many are actually in that orbital? Only 1. So this is where that exponent right here comes in handy, because this is the 4s2 orbital, but I don't want to tell everyone that's reading this that I have 2 electrons there, because I don't. I only have 1. So that's where that exponent tells you how many electrons are present in the orbital. And so just like we did with these marbles, we're going to do with electrons. So imagine all of those little dots now instead of marbles. Those were electrons around your nucleus. All right, and we have to work in order. As we fill one cup up, we go to the next cup. We go to the next one. And some of those cups can hold more than others, and some of them can hold less than others. And so we work in order until we have placed all of our electrons, until we run out of electrons to place. All right, and so that's why you'll see here 6 and 7 don't have numbers in these boxes. If you forget to leave those empty, you're not going to end up getting anything wrong because you'll never make your way over there. So if you added up all of the exponents that's in your electron configuration table, it would get you to 118. If you look at your periodic tables, 118 is the largest atom that you see. All right, so 118 electrons is what you would need to place. Now, if you look at some other periodic tables and some other electron configuration diagrams, some of them you will see an 8s2 or a 60 or a 6f14. Right, and that's because, as you know, throughout time, and especially recently, we've discovered new atoms. All right, and with those new atoms come a higher atomic number, more protons, and thus more electrons. All right, so if you forget and you put numbers here, it's not going to hurt you. You're not going to get it wrong, but do note that you will never use them. All right, because you're placing those electrons as you work your way through. So going back, and let's actually take a look at the steps to writing electron configurations. Step 1, we are going to find the total number of electrons. Remember, this is equal to the atomic number if neutral. Neutral means that my atom doesn't have a charge. I have just as much positive as I have negative, and they cancel each other out, and my atom's neutral. You will know if an atom's not neutral because you will see a plus or a minus to the top right. All right, so if chlorine had a negative there, then I would know that I have a few more electrons. All right, so in this case, we're just looking at plain old chlorine. So that means I have 17 protons, and I also have 17 electrons to balance it out and make it even. All right, step 2. A way to help self-check yourself is to go ahead and determine which orbital will be the last to fill. What should be the last thing that I'm writing as I do my electron configuration? All right, so say you were working with beryllium. You know that S2 should be the last thing that you write in your electron configuration. If you were looking at zinc, D10 would be the last thing that you write. Maybe we're looking at silicone, P2 would be the last thing you write. So that's just a way to help you self-check yourself as you're working along. Then we have step 3. We're going to fill in those orbitals in order so that we reach the total number of electrons of that atom, just like we did with the marbles and our energy levels. All right, as one fills up, we move to the next. As that one fills up, we move to the next. You have to work in order. Follow the yellow brick road. All right, just because you don't have enough to fill it up all the way, that's totally fine. You just have some empty space in that orbital. All right, there's still electrons there, it just may not be full. So fill those orbitals in order to reach the total number of electrons. So we're looking at chlorine. Let's look at that as an example here. Following your table or your chart diagram that you drew, all right, with your arrows through it, chlorine, we said that we have to place 17 electrons. Remember, protons and electrons are equal if it's neutral. So I start with 1s2, and that places 2 electrons for me. Then I move, that one's full, so I move on to 2s2. And now I've placed a total of 4. 2 plus 2 is 4. Move on to the next orbital, because I still have more electrons to place. I need to get to 17. That's my goal. All right, so then 2p6, I've placed 10. After 2p6 comes 3s2, place 12. And after 3s2 comes 3p6. But if I were to put 6, if this were a 6, then I would have 18, and that's not what I want. Do I need all 6 of those? No, I only want to get to 17. So 3p5. All right, just like when we looked back and we used our marbles. All right, right here, we used our marbles and we had 4s1. It's okay that that cup is not full. I didn't have enough. I can't create electrons where I don't have them. So that's why you change that exponent to say, hey, there's only 1 electron in that orbital. Or for instance, when we're looking at chlorine, there's only 5 electrons in this orbital. It doesn't fill it all the way up because I only want to illustrate 17 electrons. All right. So let's do some examples in your notes. Looking at oxygen, sodium, and so forth. First thing we want to do is let's go ahead and identify the number of electrons. All of these except for aluminum are neutral. So oxygen, its atomic number is 8. That means I have 8 electrons. Sodium, its atomic number is 11. It's neutral, so I have 11 electrons. Sulfur is number 16. It's neutral, so I have 16 electrons. Potassium, neutral. Atomic number is 19. Oh, let's look at aluminum. Those of you wondering, how do I know if it's positive or negative? How do I know if it's not neutral? Well, here you see it. See that +3 at the top left noted for you? That tells you aluminum is positive. So let's think about it. Aluminum originally had 13 protons and 13 electrons. But now it's positive by 3. And remember, only our electrons can change. So if you are now positive, looking back at unit 3 when we talked about this and we used the example as positive and negative life, right? If I now have a positive life, what did I do to all the negativity? I got rid of it, right? Well, what's my negativity? My negativity is electrons. How many electrons did I get rid of so that I'm now positive? I got rid of 3. So instead of 13 electrons, I have 10. Aluminum plus 3 has 10 electrons. And then lastly, we have strontium, which is number 38. And so as we work through these, follow with me over here, because I'm going to white them out as we go so you can see the path that we're following. All right, starting with oxygen. Let's write some electron configurations. Oxygen, I'm going to start at 1s2. All right, and that places 2 electrons for me. After 1s2 comes 2s2. I have a total of 4 electrons placed so far. It'll help you to keep tally underneath. All right, after 2s2, I go to the next arrow and I start again, 2p, and it says 2p6. But if I have 6 of them, I now have 10 electrons. So that's too many. Instead of 2p6, how many do I need? I'm not going to fill it all the way up. I only am going to have 4 in that orbital. All right, so 2p4, and that gives me my total of 8. All right, let's look at sodium. Again, starting at 1s2, 2s2. After 2s2 comes 2p6. Got a total of 10 so far, 2 plus 2 plus 6. And so I need to get to 11. So I have 3s. And how many are in that s? Only 1. So there's my 11. All right, let's take a look at sulfur. All right, sulfur has 16. Again, starting at 1s2. 1s2, 2s2. 2p6, 3s2. So up to here, I've placed 12 electrons. You're adding those exponents. After 3s2, where do I go? 3p6. Well, I only need 4 more, so I've got 3p4. And that gets me to 16. All right. Now let's take a look at potassium. Again, you can follow along with me on the right as I white out these as we work through them. 1s2. After 1s2 comes 2s2. So I've worked through these first 2 arrows. All right. Then I have 2p6, 3s2. And then I have 3p6. Go ahead and tally up what we have so far. This was 10, 12, 18. We only need 1 more. What comes after 3p? Look at my arrows over here. What is after 3p? 4s. And I only need 1, so 4s1. All right. Now we have aluminum +3, our cation for aluminum. All right, so 10 electrons. I've got 1s2, 2s2, and after 2s2 comes 2p, and I need all 6 of them this time, 2p6. And then last one, strontium. So strontium is going to start. Notice all of them start at 1s, so 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. So here's the path I was following. 1, 2s, 2p, 3s, 3p, 4s. And that gets me to, I'm going to put it over top because it won't show up on the bottom, 20. But I want to get to 38. So I'm at 4s2, then I go back up here and I go to 3d10. That takes me to 30. After 3d10, I go to 4p6. So there's 36. And after 4p6, I go to 5s2. Ran out of room, so there's my little 2 there. All right, and that gets me to 38 electrons. All right, so please make sure you're paying attention to those arrows and you're following the correct path to fill these. All right, so now that we know how to write the full electron configurations, let's take a look at and compare the electron configurations of 2 different elements. Up here, I have the electron configuration for krypton of 36 electrons and antimony of 51 electrons written out. All right, and when you look at these, what do you notice? What do you notice about this? Well, if you look, krypton's electron configuration is the exact same as the first part of antimony's electron configuration. So this seems kind of redundant to keep writing it, right? So for those of you who are like, why do I keep writing this? It's the same thing over and over again. Guess what? There's a shortcut. Wouldn't it be a lot easier to, when we're writing antimony, to say, hey, it looks just like krypton, which is going to abbreviate the first 36 electrons for us. And then after krypton, we just add on 5s2, 4d10, and 5p3 in order to place the remaining electrons. So here's 38, 48, 51 electrons, and we're done. All right, wouldn't that be a lot easier to do? To use our other elements prior to abbreviate really long elements. All right, really long electron configurations. So let's take a look at how do we do this? Well, when we looked at antimony, we said, man, that's a really long electron configuration. It would be a lot easier for me to write it shorthanded. And so that's what our noble gas configuration is going to allow us to do. All right, you may also see this referred to as the abbreviated electron configuration. It allows us to shorten the electron configuration for any atom By using the last noble gas that you passed. And yes, you must use the noble gas to abbreviate. You cannot use any other element to abbreviate. All right, it must be the last noble gas. And so we'll take a look at why here in a second. So as you're doing this, step one is to find the element that you're looking at and note how many electrons. So we were looking at antimony, which is number 51, and we said it has 51 electrons. And then step two tells us to go back to the last noble gas that we passed. So recall that everything on your periodic table, all your elements are in order, left to right, of increasing atomic number. So that's what it means when it says the last noble gas that was passed. If I placed all of these elements in numerical order, what was the last noble gas that I passed before that element? All right, recall that your noble gases are all in group 18. All right, and think about what we talked about with your blocks on the periodic table and how they represented your orbitals. So here was our S block. Here is our D block. And over here is our P block. Well, what do you notice about the noble gases in terms of the P block? This would be P1, P2, P3, P4, P5, and P6. So your noble gases fill up the p orbital. Well, what happens after the p orbital? If you look at your electron configuration, after every p comes what? The next level. All right, after p, we go to the next energy level. After p, 4, 5, 5, 6, 6, 7. So for those of you who want to know the why behind everything, this is why we have to use the noble gas, because it finishes up that p orbital and leads us into the next energy level. And remember that the energy levels represent the row in which the element is on. All right, so that noble gas fills up that p orbital and leads us into the next row, and that's what allows this to work. All right, so for those of you who always need to know why, that is your why for your noble gas. All right, so let's look at why we use krypton here. All right, we found antimony, which is Sb, and in order to find the last noble gas is just go up one row and all the way over, and you'll find your noble gas, no matter what it is. So let's take a look at some other examples just so that we can identify those noble gases. All right, if I'm looking at chlorine, I'm going to go up and over, and I get neon. If I'm using calcium, I'm going to go up all the way over, and I end up with argon. All right, if I'm using iron, Fe, go up all the way over, and I use argon again. Let's say I'm using carbon, and I want to write the electron configuration for it using the noble gas abbreviation. So carbon, I'm going to go up and all the way over, and I would use helium. If I was using iodine, I'm going to go up all the way over, and it's krypton. Right? If I'm looking at lead, go up all the way over, and I would use xenon. All right, so you must use the noble gas. Noble gas is that last row in the P block. All right, then step 3, write the symbol of the noble gas in brackets. So whatever noble gas you use to abbreviate, write it in brackets. So for antimony, remember we were looking at Sb, antimony. The last noble gas that I passed was krypton. All right, so I'm putting krypton in brackets, and I'm abbreviating that electron configuration. Make sure you notate how many electrons krypton abbreviates for you. And then continue with your electron configuration using the row number that the element is in. All right. So again, we're looking at antimony, which is SB. All right. If you look at your periodic table, SB is in row 5. Go over here. 1, 2, 3, 4, 5. Row 5. All right. So we start off that abbreviation with 5. And remember, we always start with the s orbital. And from there, you continue on until you reach the correct number of total electrons. So notice we had 36 that was abbreviated with krypton. 5s2 got me to 38, 40, 10, 48, 5p3. There is my 51. All right, so let's take a look at what each of these things represent, and you should label this in your notes. All right, we have krypton. This is the last noble gas that was passed. All right, up and over. Last noble gas that was passed. Then I start with 5 because this is the row that the original element, which was SB in this case, is in. All right, and then we always start with S. Think S starts with S, always start with the S orbital. And then we just continue on until you reach total number of electrons. All right, so you pick up from 5s2, and if you'll look at your electron configuration chart, picking up at 5s2, and after 5s2 comes 4d10, 5p6, but we didn't need all 6 of them because we only needed to get to 51. All right, so let's take a look at some examples. All right, your examples here are aluminum and strontium. All right, so if I look at aluminum, aluminum has 13 electrons to place. So step 1, note the electrons. Step 2, find the last noble gas that was passed. So find aluminum and go up 1 row and all the way to the right. And that takes us to neon. And so putting neon in brackets abbreviates 10 electrons because that's how many electrons neon has. And then I start with the row number in which aluminum is in. Aluminum is on row 3 of the periodic table. And I always start with S. So 3s2, that gets me to 12. After 3s2 comes 3p6, but I only need 1 more, so 3p1, which gets me to 13. And you're done. All right, last noble gas that was passed, row number that the element's in, and start with S and continue. Now let's take a look at strontium. Strontium has 38 electrons. So we're going to start with the last noble gas that was passed before strontium, so 38, 37, 36, or go up 1 row and all the way to the end, and you will see krypton, which abbreviates 36 electrons for us. And then we start with the row number in which strontium is in, Strontium is in row 5 on the periodic table. And we always start with S. Well, 5S, which can hold 2, and that leads us to 38. All right, let's take a look at one more example here, just in case you all need it. Let's look at another example. Let's look at phosphorus. All right, phosphorus has 15 electrons. And in order to abbreviate it, we want to go up and over, so we get to the last noble gas that we passed, which is neon. All right, and neon abbreviates 10 electrons for us. And from there, we pick up with the row that phosphorus is in. Phosphorus is in row 3 on the periodic table. Always start with S. So 3s2, that gets me to 12. After 3s2 comes 3p, and I only need to get to 15, so 3p3. All right. And let's take a look at one more, just for good measure to make sure we are good. All right. Let's take a look at lead. All right. PB. And PB, lead, has 82 electrons. That would be a long electron configuration to write out. So thankfully we have our shorthand here. All right, 82 electrons. So find PB on your periodic table, and let's go up and all the way over. So we abbreviate it with Xe, xenon. And xenon has 54 electrons. So that's how much is abbreviated. From here, in order to continue and get to 82, I pick up with the row number that lead is in. All right, if we follow it over to the left, you'll see that lead is in row 6. We always start with S, so 6s2, which is 56, and then we continue from 6s2. So after 6s2, we go to the next arrow and we get to 4f14, which takes me to 70. After 4f14, we go to 5d10, which gets me to 80. And after 5d10 comes 6p2, because I only need 2. So there's 82 electrons. And if you'll notice, it's in the P block on the periodic table, and it is the second column over. All right, so all we did here was follow the electron configuration table, starting with 6s2. And you pick up there and you continue, because Xe has abbreviated all the way from 1s2 until right before 6s2. So you don't need to write that. All right. This is the biggest spot where I see people mess up, is making sure that you start with the row number. Never, ever, ever start with 1 when you're writing the noble gas configuration. You always start with the row number. Always start with row number of original element, not the noble gas, the original element. All right. And that is electron configuration.